Alrighty, so in this video, we are going to be talking about the ratio test. We are going to have the series a sub n be a series with non-zero terms, and the series a sub n will converge absolutely if we take the limits from n to infinity, and then we take the next term, so in this case a sub n plus 1, and the original term a sub n. If this is less than 1, we know that it converges absolutely. Now, the series would diverge if my limit is greater than 1 or infinity, and if my limit is equal to 1, then it's inconclusive, which means that we're going to have to figure out another test instead of using the ratio test. All right, so with the ratio test right here, it's good for any factorials and alternating terms right here. So like number 1, we have a lovely factorial that we're going to be working with. All right, so we have the limit as n approaches infinity of my next term, in this case n plus 1. So what I'm going to do here is for every n I see, I am going to have an n plus 1. Now, because I'm dividing, this is essentially multiplying by the reciprocal. So now I have multiplied by n factorial over 2 to the n. I'm going to focus on the 2 to the n plus 1 and the 2 to the n. If I were to use properties of exponents, I'm going to get a 2. And then I have n factorial, and then I have n plus 1 factorial. Now, as a reminder, n factorial is the same thing as saying n times n minus 1 times n minus 2 times n minus 3, and so forth. Whereas n plus 1 factorial is going to be n plus 1, n minus 1, n minus 2, and so forth. And you'll see that everything will cancel out except the n plus 1. So now I have the limit as n approaches infinity of 2 over n plus 1, and that's going to be 0. Since 0 is less than 1 right here, this tells me that my series absolutely converges. So absolutely converges. All right, we're going to do the same thing with number 2. I am going to take the limit as n approaches infinity, and then for every n I see, I'm going to have an n plus 1. That is essentially n plus 2. Then I'm going to multiply by the reciprocal of my original term. And then I am going to go ahead and try to manipulate this. All right, so I have the limit as n approaches infinity. I'm going to look at my 2's right here. So I have 2 to the n plus 2, and I have a 2 to the n plus 1. If I were to subtract that, I'm going to get 2 to the n, so that's just 2. Now, if I do 3 to the n and the 3 to the n plus 1, and if I subtract them, I'm going to get a 3 to the 1 at the bottom. So now I have 2/3. So I have the n plus 1 square, and I still have the n square. Now remember that since this is a degree of 2 and this is a degree of 2 and they're same degrees, I'm going to look at my coefficient, and that's going to be 2/3. Since 2/3 is less than 1, we know that this series right here converges absolutely. All right. For number 3, I'm going to go ahead and take the limit as n approaches infinity of the square root of n plus 1, n plus 2, and then multiply by reciprocal of my original. And then notice how here, if I multiply this out, I'm going to have n to the 1/2, and I'm going to have n. So that means that I have an exponent of 3/2 with a coefficient of 1. Likewise, right here, I have the square root of n and n. I'm going to have an exponent of 3/2 with a coefficient of 1, which means that my limit is 1. Because my limit is 1, this means that this is inconclusive by the ratio test. So that means I can't really use the ratio test. Probably have to use something else. Right. Now, we kind of know by the nth term test, which is just this right here. We have n to the 1/2. We have n that will be 0 in terms of my limits right here, which means that I can't use the nth term test. Okay. Can't really use the integral test either. So what we're going to have to use is probably a comparison test with the square root of n and n plus 1. So let's think about what we can compare this to. Let's say the square root of n and n. That's bigger. And if I were to look at this, I have n to the 1/2. I have n, which makes 1 over n squared. We know that this is a p-series test, and this is going to be divergent because the exponent is less than 1. The p-series test. All right, number 4. Once again, I am going to go ahead and take the limit as n approaches infinity of my next term. So n plus 1 times the n plus 1 all over negative 3 to the n plus 1 minus 1, which is just going to be n multiplied by the reciprocal of my original. And I play around with it, see what we can do. So now I have the limit as n approaches infinity of, let's say, negative 3 to the n minus 1 and negative 3 to the n, which means that I have a negative 3 to the negative 1 up top. My pi to the n plus 1 and my pi to the n, if I subtract them, I'm going to get pi up top still. Then I have n plus 1, and then I have n. Well, the n plus 1 and the n, since we have the same degree on the top and the bottom, I'm going to look at my coefficient. In this case, my coefficient is going to be negative 3 to the negative 1 pi, which if I were to do this, it's going to be negative 1/3 pi, which is essentially the same thing as 1/3 pi. Now, if I were to think about pi over 3, remember that pi is 3.14, so this is going to be 3.14 over 3, which is going to be a little bit greater than 1. Since that's going to be a little bit greater than 1, and we know that this right here is going to be divergent based off of my ratio test right here. So this diverges by the ratio test. Oops, not that one. This one right here. Diverges by the ratio test. Yay! All right, number 5 and number 6 are going to be the same thing. You're going to find the next term, n plus 1, multiply the reciprocal of the original one, and then see if it's either greater than 1 or less than 1 and call it a day. That is essentially the ratio test. In the next video, we'll talk about the root test, which is going to be very similar to this in terms of how we go about things.